All right, folks, let's get started. So welcome to our winter seminar series. So I'm Krishnan Mahesh, faculty in Naval Art, Mechanical and Aerospace, and today I'll talk about our group's work on the high fidelity simulation of multi-physics turbulent flows. So this slide describes the challenges in simulating turbulent flows. The first being that they are three-dimensional. And unsteady, with a very wide range of length and time scales. And to illustrate that point, there are two images on the slide. The first is that of a bathtub jet. The second is that of a jet from an erupting volcano. They're both similar flows, but clearly the flow of the jet that comes out of the volcano has a much wider range of length and time scales. Why is that challenging? Because if you try to compute these flows that have a wide range of scales, you need to have small grid sizes over a large domain. You need to have small time steps for integrated for a long period of time. And so there are different levels of approximation in simulating turbulent flows. The first, assuming you know the governing equations, is called direct numerical simulation. You just discretize the governing equations on a computational grid, resolve it, and compute it. Now, as the flows become higher Reynolds numbers, that's not practical. And so there is the approach called the RANS, where you try to solve for the time of the ensemble averaged flow. And the issue with that is now you need to model the unsteady effects of the turbulence. There is an intermediate approach called large eddy simulation, where your spatial grid resolves the large energy containing motions and your calculation is unsteady, but then you have to model the smaller circuit scales. And so LES is what we are developing for complex multi-physics flows. So what do simulations enable? What is the sort of overall objective? In a nutshell, we hope that simulations become reliable enough that enable us to go from model scale to full scale. What do we mean by that? Well, the classical approach in engineering is to perform small scale experiments, right? Say water tunnel experiments, whose results we then take and scale to full scale. Now, if you look in the marine domain, the largest water tunnel that we have, there is a big LCC in Memphis. It's an order of magnitude smaller than a full scale, something in the ocean here. Right? Scaling is challenging for as the physics gets complicated. For example, cavitation, right? Where liquid becomes vapor. Cavitation starts from nuclei, which are submicron. Right? And then you go all the way to something, all the way to bubbles, which are say tens to hundreds of microns, and your model experiments to full scale. Now, when you go from a bathtub or your water tunnel out to the ocean, the size of the bubbles remain the same. The nuclei remain the same, but the length scale, everything else is scaled up, which makes scaling difficult. Yeah. And so the question we ask is, can simulations assist, complement, replace some of this testing? And if yes, can simulations help us develop improved scaling laws? And for this to happen, the simulations need to be reliable. Numerical methods matter when we try to simulate turbulence, and this slide tries to make that point somewhat visual. So what you're looking at on this slide are results from computations of the flow in a gas turbine combustor geometry, right? So there are two figures here, both show you contours of velocity magnitude, and these are simulations on the same computational grid. We've kept the grid the same, but changed the Reynolds number. The one on the bottom corresponds to a lower Reynolds number. The one on the top corresponds to a higher Reynolds number. Now, if you compare these two figures, you see how at low Reynolds number, you have what looks like a jet coming out of the central passage. At higher Reynolds number, you have flow coming out going radially, and you have a big recirculation region. So the flow is clearly different at Reynolds, the two different Reynolds number. Now, in this case, this is a physical effect of viscosity. But what is the relevance of this? And the point we are trying to make here is that often when the geometries get complicated, simulations can become unstable. And so numerical dissipation, introducing a little bit of dissipation as a way to to stabilize the simulation, right? And so numerical dissipation on a coarse grid could potentially, depending on the flow, produce the same effect as low Reynolds number. And so you end up with a flow that's topologically very different. Yeah. This slide also shows the scaling issue, how something at a low Reynolds number at small scale could fundamentally be different from what you have at large scale, right? And hence the need for that promise to be realized. Now, why make a production of this? So what is the point that we are making here? It is that at high Reynolds numbers on coarse grids, simulations can become unstable if the numerics are improper. And like I said, one might stabilize them by introducing numerical stabilization, but that can affect the result. So if you don't have dissipation, you become unstable. If you introduce the result changes, what then do you do? Yeah. So one way to address that problem is by developing methods which have the proper nonlinear properties. For incompressible flow, one such property is what's called discrete kinetic energy conservation. Okay. So what is meant by that is the following. If you took a flow, an incompressible flow, you conserve mass and you conserve momentum. Automatically, the two automatically imply that you also conserve kinetic energy in the inviscid limit. And it's chain rule that gives you that property. But the thing is, discrete operators, numerical methods don't satisfy chain rule. So conserving mass momentum doesn't automatically imply you conserve that. Now, why is conserving kinetic energy important? Well, it's a quadratic quantity. So if you conserve that, then the stability of your solution is determined by what you do at the boundaries, which is something that you impose. Yeah. And so the essence of it is, some years ago, we developed a numerical method that has that property of the governing equations on unstructured grids, which allow complex geometries to be represented. Okay, so that's been hugely enabling for us. So I wanted to show you a couple of results in a very canonical configuration to show you what that means in reality. Okay, so this is an example of where we are computing isotropic turbulence on a very, very coarse grid, 16 cubed. It's very coarse. All right. Now, if you just, and here's what you get. The figure on the left shows you the kinetic energy is a function of time. Now, for isotropic turbulence, it's just you set up this turbulence, you let it go, and times the kinetic energy just decays. The decay rate depends upon the Reynolds number. High Reynolds number, lower decay rate. Okay. And so if you look at the left, kinetic energy versus time, the Reynolds number is increased from 10 raised to 2 to 10 raised to 9, 10 raised to 6, 10 raised to 9 are practically inviscid on this grid. And so you see how the flow remains, the kinetic energy, the higher Reynolds numbers remains pretty much constant. Okay. Now, at this point, you don't have any turbulence model. But because the grid is coarse, it's not enough to resolve the flow. So what's happening is you have these large motions that you're capturing, but then there's all this unresolved stuff that's actually transferring the energy to their scales. And that's what the subgrid scale model is supposed to do. Yeah. So here on the same grid, you're turning in your model, and you see how the decay rate goes up, especially the high Reynolds numbers. So your solution is seeing the effect of the model. And that's what you want. So you want Reynolds number sensitivity, you want the solution to be sensitive to the model. If you instead we have some numerical dissipation, then the solution will decay at a rate determined by the numerics and not the model. Yeah. So this is the what you get. Now, even if you have a method that has nice properties, if the measure is not fine enough, you are not going to represent the correct physics. So I wanted to use this problem to make that point. So what you have here are two vortices that are interacting with each other. I'll describe this problem in some more detail later on. But you see how this weaker vortex wraps and is around the stronger one and is stretched by it. Now, when a vortex is stretched, you might imagine that its core size decreases, right? And so resolving it becomes harder. Now, why do you care about this problem? When the vortex is stretched, you care about it because when the vortex is stretched, the pressure in that core really drops. And when the pressure drops, that causes cavitation to incept. And that's what you care to predict. And so the implication is when you try to do this problem, if your mesh is not fine enough to resolve that vortex core when it's being stretched, your solution is going to say, hey, there's no cavitation occurring here. Well, the experiment is telling you, no, there is. So this is a scenario where the important thing, the thing you really care about, is happening at very, very small scales that become impractical to resolve even with a numerical method that you like. And so your solution strategy has to be one of modeling that subgrid scale, low pressure events that trigger inception. And I'll touch upon that later. Yeah. So these are sort of the three main points that I wanted to make here. We are interested in solving flow over things that move. And so we've developed in recent times, these two papers here describe the details, a methodology for moving bodies, multiple moving bodies. It's called unstructured overset. Unstructured allows you to do complex geometries. Your elements can be arbitrary. And overset refers to basically solving for the flow on number of meshes that can move. And so to illustrate that point, these specks, this is the flow of many particles in a turbulent channel. Those little specks you see on the top, you zoom in, each of them is a particle. And the flow around each particle is resolved by this computational grid. So what's happening here is you have many computational meshes that are moving and rotating and interacting the background mesh, and we are solving for the flow and transmitting information between all of them across multiple processors. That's the essence of an overset method. And the significant challenges there have to do with numerical conservation. How do you conserve mass, momentum, have these energy conserving properties and all these different grids? And the second is parallel scaling. As a number of meshes and so on increases, are you effectively making use of multiple processors? And so these techniques had to be developed, and solutions are developed to them in those two papers, using ideas drawn from things ranging from techniques used in video games, for example, to handle how things are cut and so on and so forth. And that resulted in this methodology. And so in today's talk, I'll show you some results from this sort of a capability. You saw many particles. I just wanted to show you one example that illustrates both the sort of the detail that Wyatt paid attention to in terms of developing this and in developing this capability. So this is an example where you have one particle. It's dropping, and then you see it rebound from the bottom wall. Yeah, you can imagine, right? If I just took a particle and dropped it on the wall, the pressure is going to increase beneath it, right? It's going to squeeze fluid out, and that's going to affect, basically, it's going to slow it down, then it's going to come impact, and then keep bouncing, right? And because there's viscosity there, you're going to have a restitution. Every successive bounce is going to be smaller. Yeah. And the thing is, because you have a mesh that's resolving the flow around that particle in great detail, the mesh itself, the flow, your solution captures those details. And so what is shown in this figure is the vertical velocity compared between our simulation and an experiment by Contre et al. The agreement's quite reasonable. Yeah. So just wanted to show this as an example of the microphysics that we care about even when we do these large scale problems. That's what makes a large scale simulation results reliable. So I wanted to show you an example that illustrates a similar sort of physics being captured within the context of a larger problem, right? Enabled by this unstructured capability. So these are LES results of flow over an appended hull, right? So it's in straight ahead, flows from left to right. That's the sail. Those are your appendages. The contours here are velocity. And this gray, the black and white on the surface are really skin friction. Yeah. So it's fluid. Think of it as fluid very close to the surface. It's the integral effect of these near wall streaks that gives you resistance or drag as you move through the water. Okay. Now on this body, you see how you see this little line here. Zoom in. This is what it is. So it's a tripwire. Yes, tripwires are used in experiments to get the flow to try and get the flow to go turbulent, so that the flow is representative of what happens at higher Reynolds numbers. Right. So what we are now able to do, so it's been known that tripwires can affect the flow, and depending on the range, it's not always clear what they're doing to the flow. Now we are in a position to resolve the tripwire using your computational grid, eliminate it as a source of uncertainty when we compare and when we scale our results. And that really is what is shown here. Okay. This here shows you, it's one comparison of the results. These two papers by Nick describe these results, describe the simulations. It just shows you how the pressure along the hull between simulation and experiment matches. And so what are these results good for? So in terms of pushing the limits to where you can resolve handle the tripwire, it's motivated us to look at these complex flows a little differently. In that, of which one idea is we think it makes sense to look at these flows in streamline coordinates. Typically, when you look at a flow, imagine taking a model like this, putting it in a tunnel. You can choose a coordinate system that's tunnel centric and say, hey, flow evolves like this in X, Y, Z. But then the geometry you say is rotated. So a more natural thing might be, hey, choose X or theta, right? And what you'll find is neither of these is natural as far as the flow is concerned. But when you think of the flow in terms of streamlines, right, you reduce one degree of freedom, and it allows you to see things and collapse them and so on more naturally. So this is an idea that we are proposing and developing for other flows as well. Another thing I draw your attention to is you see the flow on the sail looks like it's going from laminar to turbulent. That's transition on the sail. And one of the things we learned here is that transition on the sail is important. And I just wanted to show you that one result here. So the experiments that we were comparing to had a bunch of pressure taps on the sail. That's what, the P1, P2, that's what that is, right? And so we compared our results to the experiment at each of those taps. So if you look at any one figure like this is the pressure. Cp as a function of x over c along this purple line. Okay, the experiments are the symbols. The solid line is us, right, where we just computed the flow. Okay. And the dashed line, the red line is us, where we tripped the solution on the appendages as done experimentally. Now, when we first got these results, and this is one station, I'll just show you some more. I'll show you a second and then some more. When you first got these results, it was tempting to say, that's good enough. Right. But then you look at all the stations and you go, looks like, look at the third, look at the fourth. It looks like there is something systemic, right, in terms of the deviation. And what we found is that when we trip the flow, the pressure goes basically through that tap, not just at one station, but throughout. Okay, so tripping on the sail is important. And the reason is the sail is smaller. So even though when the Reynolds number based on length is larger, the Reynolds number is lower. And so you expect that sort of a thing. Yeah. So these are the sorts of things that we can now do. Wanted to show you a couple of results on the application of this capability to what's called a prolate spheroid. It's a model for the hull of the body. And right now there's a big experiment being planned whereas that Ellie knows a lot about. Anyone who's interested, talk to her about the experiments. They're really interesting, really cool experiments of really large spheroid that's going to be tested in the LCC. And the instrumentation on it is really wild. And so LES is at a point where it's considered reliable enough to work with the experimentalists in the planning of things. Okay, and so while the experiments will be, so LES was used to inform trip design in these high flow experiments. How do we trip the flow at angle of attack, and how do we, and so on and so forth. Now, while that was going on, in parallel, we were performing simulations of experiments that were done much earlier in the Simpson group. And these are results from those simulations, right? And a couple of things that I wanted to point out. You see what looks like a ring here, right? Is actually 238 posts that those experiments had used. And because of the overset thing, we are able to attach grids to each of those posts and just resolve the flow. Right. So it eliminates that if you don't agree with the experiment, at least it's not because you didn't resolve the tripping geometry. It's something else that's off in your simulations, right? And these black and white things, again, you see these things, that's a skin friction. So this is the wake of the post. And because of the angle of attack, you have high pressure here, low pressure there, the fluid wants to go, you establish a cross flow, yeah? And so the wakes are being transported in that direction. And qualitatively, if you look at the flow, you see how it's relatively more quiescent here, has waves, and fully turbulent here, right? Then these boundary layers separate and form these big vortices that are unsteady, and they affect the loads on this thing, yeah? So this just gives you a qualitative sense of the flow. What were the simulations good for? Well, they provided a regime map of the flow. They allowed us to comment on the nature of the complexity of the flow over the body, and that's what is responsible for resistance as well as the loads. It revealed the importance of turbulence to laminar transition. And again, this was another problem. Again, look at it in streamlined coordinates, seems more intuitive, easier to think about. And we looked at the span of the effect of Reynolds number and angle of attack. This is at 20 degrees. We varied the angle of attack to say, hey, how does the flow change? For the same angle of attack, we vary the Reynolds number. How do things change? And the flow is amazingly rich. And I just want to share a couple of results with you on that. So this here is the qualitative effect of angle of attack on the flow over a spheroid. So have a look at one of these figures, and I'll tell you first explain what we are plotting here. So you have the spheroid that looks like an egg, right? What you've done is to unroll it, if you will, and put it on a plane. So x equals 0 is still, if you took this as a spheroid, x equals 0 is the leading edge. X equals L is still that trailing edge. phi equals 0 is the bottom, the windward side, phi equals 180 is the top. Make sense? That's what you've done in unrolling it. And so here, in all three plots, the Reynolds number is the same at 1 million. You've changed your angle of attack, 10 degrees, 50 degrees, 90 degrees, right? And your first impression is you see qualitatively how different the flow is when you just change the angle of attack. Yeah, that's the first main point that we're trying to make. And what is the nature of the difference? Well, if you look at it a little more closely, you go, at 10 degrees, you see the flow is turbulent, basically on the bottom and the top, right? As soon as you went to 50 degrees, you see how most of the bottom here looks like it's laminar and unsteady, right? And you see there's multiple separations here on the leeward side. Yeah. And then you go to 90 degrees, and 90 degrees, this is your egg, right? And flow is doing this. So it's clearly it just separates completely. It's laminar here, and there are foci of attraction and separation. Yeah. So angle of attack makes a huge difference. And one of the things that came out of this is how 50 degrees, close to 50 degrees, is like a critical angle where the flow topologically changes. It goes from being here you're attached, right, at 0, 90 are totally separated. Somewhere you're going between the two. That's the essence of the transition between the two. And these two images show you the effect of Reynolds number. Here you kept the angle constant at 50 degrees and just change your Reynolds number. On the left, you're 1 million, right, you're 4 million. And again, do you see the first impression is qualitatively how different the flow is, right, as you increase the Reynolds number. And if you look at the low RE, yeah, you flow here basically looks laminar, and there's a slow moving separation line. As you increase your Reynolds number, you see how the separation line becomes more steady. Right. And then you have these wave-like things in the flow. So these things, why they happen is it's a source of huge interest to us. How does a transition occur from one regime to another? Are there regimes? There are experiments that show when you have these things, you saw those big vortices on either side, they can be asymmetric. So they form in one side and then they just want to stay on one side. And that's a huge deal, right? You can imagine if your vortices are, if you make a big vortex and to one side, you're going to one side. Your loads are all pushing in one direction. That's a problem. Why does it happen? When does it happen? Why do these waves form? Can we take this data? Can we take measurements away from the wall and assimilate, predict what's happening near it? And then think about it. Future pressure fluctuations, right? What is their nature? Skin friction, what is their nature? What are materials of the surface? What are they going to look like? And we do little things near the separation points and so on to change the topology of the flow. So thinking of all of these things in the context of this, and in the context of this flow is how we're thinking about it. And this thing is stationary. You don't just stand still in the ocean, you move. So once you start moving, now you have unsteadiness in the mean, and that changes everything, right? Even more. So that's the richness of this problem that we're hoping to look at down the road here.
So you are in the range of 180. What about the other half? Is there any oscillating?
In the mean, they're axisymmetric.
Yes, but instantaneously, do you see any?
Say a little loudly.
Instantaneously, do you see any regular asymmetry oscillating between?
We don't see the vortices going, just shedding here and shedding here so far. But that's something that we plan on looking at closely. I think it has to do with small changes in the leading edge radius of curvature. I think can greatly affect us. Any changes stagnation.
I guess follow the so if you have asymmetry in the vortices, even if your boundary condition is not asymmetric, why do you think that occurs in the first place?
So this asymmetry has been observed in other problems like Jetson cross flow and so on. Yeah, and we have written on that. That asymmetry originates from small asymmetries, which can amplify on the asymmetry. So here, this is just my guess, right? But you have a very small radius of curvature. Really, the stagnation point, its location is very important because the flow comes, stagnates there, then accelerates on either side, right? Yeah. Now, if I have a small asymmetry near the leading edge or a small asymmetry in the free stream flow, the stagnation point is off a little bit to the side, right? Then it's quite stable and happy to sit there. Flow will just accelerate on one side, it's quite happy to sit there. So these flows, slender bodies in general, are quite prone to these things, I think.
So these asymmetries, do they exist in numerical simulations as well? Because they're
harder to get in numerical simulations because you don't have this. So you have to, but understanding them and what their source is of huge interest. Even what I'm telling you is speculation. Yeah, I don't know. But these things are known to exist. Yeah, there's a recent review paper that looks at the asymmetries. We've written on Jetson cross flow and asymmetries that maybe we know a little bit more.
I see that a lot in experiments as well, so.
Exactly. So cavitation, important example of multiphysics. So liquids cavitate and cavitation is important. What is cavitation? It's the conversion of liquid to vapor in regions of low pressure, right? And the reason you care about cavitation is twofold. One is when cavitation just forms, it's very noisy. And this sound that you're hearing in the room, it's coming from what you're looking at on the left is you're looking down on a hydrophoid that's placed on the floor of the tunnel. It makes a tip vortex, right? Finite rings make tip vortices. They cavitate. The sound you're hearing is from that vortex. Imagine this happening behind a propeller when you're underwater. Yeah, something you would not like to happen. Now, when the cavitation is large, it can cause coatings and so on to erode. That's what's happening on the right-hand side. So these are the two reasons to care about it. So the question is, can we simulate cavitation and use it to predict and hopefully then control or design for these things? So I want to share with you a couple of examples in both inception as well as the erosion regimes. The first has to do with inception has to do with cavitation, inception, and ducted propulsors. So this figure here on the right, you can visualize it. What you're doing, you're looking down on the blade of a propeller, which is moving in the direction indicated by that omega arrow. So do you see it? This thing is kind of moving in that direction away from you. So when you do that, you have higher pressure on the right-hand side and lower pressure on the left, right? And so flow wants to do this. It wants to come from the high to the low pressure region. That forms this thing called the primary vortex. In addition, there are these things that are most prominently seen near the trailing edge that this figure calls as secondary vortices. Okay. Now, the reason you care about this problem, what you care about is inception in these ducted propulsors. At what free stream pressure do you start hearing noise? Does inception occur? That's the engineering problem. Yep. And there's past work, experimental work on this, which shows that the tip vortex in ducted propulsor, it's known from experiments and propeller designers, the tip vortex is weaker in ducted propulsors compared to the open prop. And furthermore, when it comes to predicting inception in these ducted propulsors, the inception is due to the interaction between these vortices. Yeah, and cannot just be predicted in terms of the strength of the primary vortex. Yeah, so the question is, can we get these interactions right to get the scaling right from small model to full scale, right? And the question we ask is, can LES predict this problem? And if so, can it guide us towards predicting scaling of inception of this problem? So we are working on simulating this problem, and these are simulations done under the conditions of experiments performed some years ago. And this slide basically compares our simulations to the experiment. The quantity, what you're looking at here is basically, you're looking at a plane just downstream of the propeller blade. Okay? The quantity in the figure on the left, you're looking at the mean vorticity. On the right, you're looking at the mean axial velocity. This is the experiment, that's the LES. And for a more quantitative sort of a comparison, what we've done in these plots is to extract profiles at these 5 stations and compare the simulations to experiment. And we say, okay, the agreement is reasonable, okay, between the two. So given this agreement, and I mean, we've done other comparisons and so on, we've looked at the flow in some detail, and I just want to share a couple of those results with you. What are the insights? Okay, you computed it, so what? You know. And so the first is that LES provides some insight into the tip cap details, right? And so one of those insights is that the interaction isn't just between one vortex that's a primary vortex and one vortex that's a trailing edge vortex. Instead, what happens is that what the blade does is to shed vorticity through a number of fine scale and counter rotating vortices that interact with the primary vortex. So let me explain this figure for you here. What you're doing is zooming in this region of the blade, right? The gray that you see this gray thing here, that's a primary vortex that sheds upstream. It's unsteady, does its stuff. It's a little bit beneath the blade, the tip of the blade. Then the blue and the green are these small vortices that are shed from the top here. And blue and the red. And they're colored as blue and red to show red indicates co-rotating, to indicate the direction of rotation, right? So blue and red rotate in opposite directions. So when two vortices rotate in opposite directions, they're counter-rotating, they interact more strongly. And so it's a combination of these interactions that allow that determine the low pressures and inception. So this kind of detail allows you to evaluate quantitatively suggestions that have been made on how inception occurs in these things, right? The next thing I want to share with you is if you have the flow field, you have the pressure field. Cavitation occurs when pressure goes below vapor pressure. And so you can examine your solution to see, hey, what are the statistics of when pressure goes below vapor pressure and where are those regions happening in the vicinity of the propeller, right? You would expect inception to happen in regions where the pressure goes below vapor pressure the most, isn't it? And if you have that, then you go, okay, what is the value of free stream pressure at which I go below vapor pressure the most? That's when I'm likely to see inception. Does that make sense? Yeah. And so that's what's done here. So basically, what's done in these three figures is that you're looking at your pressure field to decide on the value of a free stream pressure. These are incompressible calculations, right? So the absolute value doesn't matter, difference matters. So for a given free stream pressure, what are the number of times pressure goes below a threshold, right? And you examine that as a function of the threshold. Does that make sense? As the threshold gets lower and lower and lower, you'll have fewer and fewer events, isn't it? So that's what's done in these three figures. Okay, you're plotting a PDF of low pressure events for a threshold of -6.2, 7.2. So you're dropping a threshold as you go from left to right. Okay, and this figure is clear, isn't it? It's downstream of a blade of the prop. Now, the first thing you see from this is, do you see how when you look at the low pressure events, it looks like you have a primary vortex interacting with the trailing edge vortex, just like the experimental visualization of the cavitation, even though the instantaneous flow is much richer. Yeah, but like this, right? So your PDFs of pressure start to look like that. And then if you look at the number of events, okay, if you look at the number of events, they go from 1.2 million to 5,000. Okay, 5,000. And so if you just took if you said, okay, if you took this 5,000 because when does inception occur? It's like saying, when does transition occur? There is some arbitrariness in that definition. If you just took this value of sigma, the free stream pressure at which you have 5,000 events, right? And you plot it along with the experimental data, our simulations are at lower RE, it shows, it follows the trend. Now the question is, does this extend to high RE? Yeah, because this figure is what you want to predict. What is a free stream pressure at which you might consider the flow to have been separate? So these are the ideas that go into it, and these are the physics. Okay. Now, we said earlier that when you have a cavitation occurring, it occurs in these, in small regions for very small instance of time. And if your mesh isn't fine enough to resolve those small regions, you're not going to get the pressures that are low enough for cavitation to occur. What do? Now you've got to model explicitly the subgrid scale low pressure events such that you get cavitation. And so that's work that we're doing. And I'll show you results in the context of a problem which has been experimentally studied here at Michigan, where you have two hydrofoils that produce these stiff vortices that interact, right? And in the region of interaction where the weaker one is really stretched, that's where your pressure is lowest. Yeah. And you'd like to compute this flow. So imagine trying to compute this. How might you do it? You go, oh, the experiment shows me inception. I'm not seeing it. Well, I'll keep refining my mesh till I see it. We did that, right? Then you go, okay, now I get it. I agree with the experiment. But now I'd like to compute it on meshes that are maybe 10 times smaller, 20 times smaller. How do I do it? How do I model it? That's exactly what we've done. Okay, so we've developed a model here that gives you estimates at subgrid scale pressure. And the essence of it is in this table here. So let me explain it to you. The pressure in kilopascal is the free stream pressure at which inception is observed. Okay. The blue here is the experimental data, which says inception has occurred between 135 to 155 kilopascal, depending upon the amount of dissolved oxygen. Okay. What I've called fine are simulations where we think we're resolving the interaction. In fact, we yeah, and everything agrees, the flow profiles and so on, we compared to the experiment, that mesh that we've used is about 1.4 billion cells. Okay. These simulations in medium and coarse, the mesh is about 10 times smaller and then even another 20 times smaller, right? And in this regime, first, if you look at the red, you see that the free stream pressure is no longer 150 or 135, right? It has to be much lower to be able to get a pressure that which it would insert. And that's not right. You make the mesh even coarser, the free stream pressure that you need is predicted to be even lower in the absence of a model. The green is what happens when you model the subgrid scale pressure. Now you see how the free stream pressure increase at which you see inception increases, right, to fall into the experimental range. And furthermore, right, if you had a perfect model, then what you predict as a free stream pressure at which inception occurs won't care what your mesh is. Yeah. But from in a practical sense, at least you should get values that are pretty close to each other. Right, and that's what you see. You get values around 140. The experiment varies in this range, and that's encouraging, very encouraging for us. Okay. And this is what the results look like, the kind of information you get in physical space. And if anyone's interested, these are the ideas that we use to model things in a subgrid scale to get the turbulence right and make it dynamic. Okay, this is the pressure in the vortices at different planes. You can see the LES gives you the low pressure, and this is what the model gives you. Okay, it gives you can compute the frequency with which you fall, at which inception is likely to occur, and plot it as a function of space. And the regions where the frequencies are highest, you go, hey, this is kind of the inception location. Yeah. And so this is work that Mehdi is doing, that we are now extending the ideas, develop it further in the context of hydrofoils, and then go apply this, the code and the methodologies and so on to develop the same thing that does this is what does the hydrofoil, is what does the propeller, the overset stuff. So we can do this and we can start thinking, applying it there. Yeah. Okay. Next, erosion, the erosion regime. So LES, again, now things are very compressible and erosive. So LES now is being applied to complement experiments on cavitation erosion. So there's a project called High-Foil in collaboration with Rock, Memphis, and us, where a big hydrofoil, right? This is the LCC, again, it's about 7 feet in core, 10-foot in span, that's a person there, is being cavitated. And there are samples placed on it that then spit. There's spitting that occurs on them because of the cavitation. That's what we care about. Yeah. So LES was used to help design those experiments, to estimate the loads and the erosive potential in the planning of these experiments. And the way the study was conducted is there's a smaller tunnel, a scaled down version of the LCC here at Michigan. Right. And so experiments were done in that. Elijah did the MLCC experiments, and so we perform simulations under the MLCC conditions to just say, hey, do things make sense? Yeah. And so this shows you how the cavity length compared to the MLCC experiments is reasonable. And then this picture, there are a couple of insights that came out from the simulations. The first being that you see how strong the pressure field is when you have erosion. This is the pressure field that causes pitting, right? But furthermore, it's propagating up and down your tunnel. Because when a bubble forms or collapses, you're changing the volume. So you make these very strong pressure waves that interact. And the second is you see how those pressure waves interact with the walls. So the effect of wind tunnel, water tunnel walls when you have large erosion is different from what happens when you're incompressible, where confinement just causes the free stream to speed up. And so these are things that we're looking at more closely. Now, these experiments don't have volume fraction measurements right now. So we decided, hey, do we really trust to get further insight into this regime of the flow? We said, okay, let's look at an hydrofoil configuration for which there is detailed, there's more detailed data, things done on a smaller scale, because the LCC is large, you can't do all these experiments. And so there were experiments done here in Michigan, where they looked at a NACA 0015 and got it to go into this very erosive regime. Can we predict it? What do we get? What do we understand? So Sungnam is doing that sort of work. And so I'll show you results at an angle of attack of 10 degrees. Okay, and then imagine and say that we are now imagine dropping the free stream pressure at a 10-degree foil for the NACA 0015 and in the same conditions as this experiment. So this is now a higher pressure, sigma is 2.6, just think of it that way. The white that you're looking at is a contour of isocontour of vapor. More white you have, the more larger regions are covered by vapor. So you see a sheet of vapor form near the leading edge where you have the suction side, the suction peak, right? And then it rolls up into a cloud and then collapses. On the vertical plane, you have pressure, and again, you see its intensity, right? As small pockets form and larger small pockets form and collapse and so on and so forth. Here is what happens when you drop the pressure. The region of vapor increases. Drop it some more, region of vapor increases some more, right? So the cavity length effectively increases. Now, what you can do is to time average your vapor volume fraction, and from it extract a cavity length, right? That's what's done here. And then we compare our cavity length to what was measured in that experiment. The crosses are the LES results as they stand. The statistics are still being gathered. So this is results in progress, and it's encouraging. Okay, the symbols and the black is the experimental data via the crosses. The x-axis is pressure. Okay, and that's really what's shown here. Okay, the agreement of the three crosses with the data is so cavity length seems to agree reasonably. And on this slide, I want to say, okay, what is the LES good for? What does it provide? Okay, you agree for cavity length, what does it give you? So you've already seen volume fraction. Sigma is the same now for all three figures, okay? You already see volume fraction on the left, right? On the bottom, you're looking at what's called Q criteria. So it shows you the fine scales of the turbulence. And you see, although the cavity is large and rolls up as a cloud, there's a lot of fine scale turbulence that goes into establishing that flow field. And this is what an LES captures, right? This moves vapor around in region, low pressure, high pressure, causes collapse, and so on and so forth. And the figure on the right is really what is useful information, because it gives you wall pressure on the surface of the airfoil. Because if you have this data and if it's reliable, then you can use this. This feeds into trying and predicting the fitting, right? Because this is the forcing function for the structural damage that gives you. So that takes us into those future directions down the road. Yeah. So that's the reason for doing these things. Furthermore, if you have pressure profiles, unsteady pressure on the surface, you can conduct it, you can analyze it, you can. And so one thing that this slide shows is imagine having probes, right? Putting pressure probes all along, say, the mid span of the hydrofoil. You have P as a function of T at all these probes. I mean, you have it over the entire foil. Then what you can do is do Fourier analysis, right? Do a spectral analysis of things over the entire airfoil as a function of distance. And so when you do that, and from that you can extract primary frequency, secondary, and so on and so forth. This year, the triangles are from Anubhav's data. These circle the solid lines. The solid symbols are us as they currently stand for the same tones. In addition, the simulations are also revealing a higher frequency, right? Which right now, which wasn't, is not available in the data that was presented. And so it raises this thing that, is it there? It raises the interesting possibility that there are higher tones also. But so far, the agreement for what we are comparing and what's available is encouraging. And this is where we are in the process, okay? All right. So we're interested in superhydrophobic surfaces, yeah, which you know there is surfaces that are quote unquote water repellent, self-cleaning, drag reducing. The figure here shows you a close-up of a lotus leaf, and you see these droplets beading on the surface. They don't wet the surface. Now, if you zoom in to a lotus leaf, that's what it looks like. Okay. Now we care about superhydrophobic surfaces from a perspective of drag reduction. All right. That is, if you had water going over a surface like this, now instead of water being in contact with the surface, you have air, right? You have gas in contact. So can the drag go down? That's the promise of it. Yeah. And so what we've developed in our group is the following. Given a realistic superhydrophobic surface, if you can scan it and give us that geometry, right, we can, using free energy principles, calculate the shape of that complicated interface. All right. That was done in this paper by Kareem and company. And we've recently extended that capability to say, if I now know the shape of that interface, can I model the drag that surface would cause, right? And Mehdi has done that. And I wanted to show you one slide on that. And here is the insight that came. This is one insight that came out of that book, which is that current literature, when it says, hey, how does superhydrophobics work, they try to correlate drag reduction to one parameter. like might be surface, RMS roughness, RMS slope, etc. But what we found is that the details aren't important, is that no one parameter collapses. It's a combination of geometrical parameters that you have to use. And here are a couple that we developed that we just call it SFC, SFP, right? We use these parameters to develop a very simple correlation for the skin friction as a function of Reynolds number. And here we are comparing to experiments. This work was done. We're comparing to experiments done by Harish Ganesh's group here at Michigan, and the surfaces that we're doing this were built with the following. We're making these predictions for surfaces that were actually built by Professor Tuteja in material science, right? So it's a collaborative project in DARPA, and the agreement of the experiment appears to be encouraging. So the future thing is, if I now zoom right to the surface, what is the detail, the turbulent details of flow that happen near the surface? That's the direction that we're thinking. So superhydrophobic surfaces are one example of, next generation surfaces. We want to call them that. But another example of more dynamic surfaces or dynamic surfaces that we care about have to do with biofouling. Okay, and so we are working on developing the capability to do coupled fluid structure interaction to understand things like compliant surfaces, right? Coatings and other things that are compliant, and things like this that are relevant to biofouling. You have things that grow on a surface. They're soft, they respond to the flow affects them, they affect the flow, and you care about computing. And how do you develop methods to predict these things, right? And just quickly go through that. And I just wanted to show you one slide saying that when you compute these flows, numerical methods matter. So the method that we've developed is one where we use numerical methods matter. Let me just say that much. Yeah. So this is an example of a very canonical problem where this thing here is it's a driven cavity. So the top lid moves from left to right. And so this big red blob, right? Imagine it rotating in the cavity and squishing around as it, the flow changes, right? Here's what happens with a good solution, okay, when we treat what's called the volume fraction field correctly or acceptably correctly. Here is what happens when you don't have the numerical gradient. You see these little specks here, these little dots. That's the interface breaking up. Here looks like nothing. But the same thing, if you apply to that problem with all the flexible things moving around, they would break and shed into the flow. Very important for integrity in a real problem. Okay. And the thing on the bottom is, again, this is just a circle. You're shearing it, it becomes an ellipse. Numerics are the difference between getting an ellipse and getting something that looks like that. Right? On the right. So just wanted to share this with you. And show you a couple of results. We're looking at DNS of a compliant wall in a turbulent channel. On the bottom is your compliant surface. That's the deflection in it. And you see how you have span-wise aligned waves that propagate downstream. This is an agreement of past experiment and numerics. And that amplitude is large enough that it is a two-way coupling. They affect the flow affects them. So it's important to have this kind of coupling. And here are some of the insights that come out of it. You can now look at the turbulent stresses, right? On the left, you have the turbulent components of turbulent energy. On the right, you have the shear stress, right, which controls the mixing in the flow. And you can observe, for example, that wall compliance increases the Reynolds stress. The cross term, something U prime, V prime, just controls the mixing of low momentum and high momentum. It changes sign near the surface, for example, which is consistent with past experiments, for example. And so we have in a one-way, so what do you do with this? Okay, we can now ask questions like, how does the structure of the flow affect the near wall perturbation in a dynamic sense as a function of frequency, and how does that affect sound? We've developed that way of analysis for one-way coupled things, and so now the idea is to go forward, answer questions like that in this two-way coupled framework. Yeah, so I just wanted to share that as an example.
It's time.
Yeah. And then biofouling, as I said, is another problem that we're actively working on. There's going on in Harish Ganesh's. So we are aligning with that. And the idea is the following, to use numerical and our tools to look at the dynamic interaction of biofouling, right? That's from Parth and Harish's experiments, and allow us to answer questions like these. How do elements shape material properties, distribution density effect, how they interact, how do we model it more accurately? How does a substrate on which these things grow affect the interaction, and how does all of this impact track and so on, right? And simulations like this, I just want to leave you with that. Is how simulations like this, if they're reliable, I mean, you have information on things like near wall pressure and vorticity and so on and so forth. Right. The key question is, well, can you believe what you're computing is the thing. And so that's the development aspect of things. But this is the potential of it is significant as we move forward. And this is the last part of my talk. So you have a simulation, you perform simulations, you have experiments. We talked about how, you collaborate, right, and assist each other. Now, another way in which you can integrate them is, can you integrate simulation data with experimental data? Why would you want to do that? Integrate, well, one possibility is use the experimental data to improve your predictions in real time. The other possibility is use the simulation data to predict things that the experiments that you have are not predicting. For example, you have right now that is of interest to us. You have experiments that do PIV or PTV that get the velocity at a few points, right? At points over a volume. That's what's shown here. These are discrete points around a hydrofoil. This is a volume of measurement, right? Typically 3D experiments tend to be in a sub-volume. Can you use those discrete measurement data to get velocities over the entire space, vorticity, pressure, and so on and so forth? Yeah, so that's a direction that we're thinking of. Integrating, assimilating this data. And I just want to summarize the ideas. We're exploring two approaches. One is what's called an adjoint approach that Gary is working on. And essentially what you do is the following. You solve a gradient-based optimization problem. So we all know least squares fitting, right? If you have data, you can fit a curve. Okay, so imagine having the experimental data here. So the actual values of velocity, whatever is being measured is one constraint. You would like whatever you're fitting to be close to it. But whatever you're fitting should also satisfy the Navier-Stokes equation. So they act as constraints to the equation. So you want to combine everything and obtain a continuous field on your numerical grid that satisfies those two constraints, right? That's the essence of it. And it's a lot easier to say it than it is to do it. So what we are optimizing is if I have this data, you have to, what are the values of the boundary? What are the initial conditions that give that prediction correctly? That involves adjoints. There's a cost in terms of how you do it and so on, so forth. So we've right now, Gary's developed the approach to do it, the algorithm to do it, and we are developing the codes to scale it up to larger problems. So then we would have a method to work with VTV data that gives you pressure, vorticity, and so on from the data. And Shenzhang is exploring pins or machine learning to do the same thing. Here, you don't solve in the idea in machine learning. In the pins approach, again, you have the data and you have some physical constraints that are right that come from your model. You don't solve an adjoint problem, but through a process of training, you get the predicted data to match what is given in, and that becomes your model, right? So how does it work compared to adjoint? Is there a hybrid that's possible that makes things better is what we'd like to do? Those are the research questions for us in the context of this problem. So just to show you a couple of results in the adjoint-based approach. This is a field of turbulence. That red square is where you're extracting data. The blue are the points where you're extracting data. On the bottom, your assimilation approach is recreating data in that subvolume. So whatever is inside the red on the bottom should look like the red on the top, essentially. Okay, and the machinery that we have to do it is allows us to calculate things like the error and so on and so forth. And this is my last slide, results on the machine learning based approach. What can it do? Just wanted to show you a couple of examples. On the left, you have what's called a Taylor-Green problem. And here you have a flow field, you're training to get the pressure without the Navier-Stokes, without the adjoint or anything like that. This is the predicted pressure. That's the exact pressure when you train on the same volume on which you have data, right? Now we are trying to push it to understand its limitations, which is going outside the range that you have. And typically we tend to think of that in one way to think of it is in parameter space, but you can also think in terms of spatial location, right? You trained on a sub-volume, you try to predict a larger volume, you don't get it right. And so future directions are to understand and develop both adjoint and machine learning approaches to develop that kind of framework where our nature of interaction with experiments is. And it's, 5 minutes more left. And so thank you. That's my talk and questions.
What is it that you cannot do? Yet.
We can do things. The question is, are we doing it right? Right. That's always say you can't trust simulations. So it's keep doing more physics and even the things I showed you. It's very much it looks encouraging, and what I'm showing you is the result. But on a day-to-day basis, everything is crashing around us, right? The whole process is figuring out what it takes to make it work. So I would not take this and go, hey, we can do whatever. On a daily basis, it's, hey, how do I do this? So it's,
For the machine learning approach with the results, it showed that it was pretty accurate on like the sample, like the training data, and then outside of that, it wasn't. How is that really helpful? Or is that just like the first step towards making it helpful in the future? If it's like correct on training data, like I would hope so.
Yeah.
Well,
So-
what does that mean? Like in the sample, being correct on the sample and not outside?
okay. What it means is us pushing ourselves to understand exactly what it can do, what it can't do. So that involves a process of defining an input and an output, and a process of scaling and the features that you look for, and so on and so forth. So that's what I wanted to share with you essentially. The adjoint is based on the equations, right? And right now, training on data, it's an approach. So what can it? They both have their strengths, weaknesses. How do you use it? I guess what I'd say is this: we are trying to answer precisely the question you asked. That's so. Yeah.
Could you please elaborate on that part where you said transforming the coordinate into the streamline of the fluid? How would you do it and why would you want to do it? I missed that part.
Oh, okay. So the question was, how would you transform? What do you mean by streamline coordinate transformation? So what it does for you is, so the simplest one way to think of it is, so take your Navier-Stokes, just take your fluid equations, write it in terms of X, Y, Z, a generic Cartesian coordinate. Now, when you write things in terms of streamline coordinates, you know that there is no velocity normal to a streamline.
Yeah.
Right. Furthermore, in a stream tube, you can conserve mass, right? And so when you take, say something from fluids, right? Take your Euler S equation and Euler N equation, the normal direction equation in 2D. You get, they become considerably simpler, don't they? You get dPdN as rho v squared over R, for example, right? A nice, the pressure gradient normal to streamlines is balanced by the centrifugal force and so on. So you reduce because you don't have fluxes across streamlines, you reduce the dimensionality of your problem. And so in the context of a general flow, so now you can derive general equations. So something like that sub-off, that hull, right? You go the flow doesn't vary in theta, so I'll derive equations along streamlines. And perhaps I can use this box, right? Let's say this were streamlined, yeah? Flow comes in like this, goes around it like this. If I looked at the boundary layer, then I might write equations along the body and then normal to the body, right? But you see how the normal in this direction is here?
Yeah.
The normal here, if the stern goes like this, let's say I gently slope this. The normal here intersects the normal here.
Yeah.
How then do I describe boundary layer growth? Whereas on the other hand, if I went in streamline coordinates, I can have one coordinate that describes the flow here to here.
Yeah.
And intuitively, just thinking about it allows you to think of the flow as saying, there is a mean direction in which the flow is moving over this thing, and then turbulence causes it to diffuse across.
Yeah.
And so that's the value, I think. It's a more physically natural thing. Instead of attaching a coordinate system to your wind tunnel or attaching a coordinate system to the body, you're defining a coordinate system in terms of the flow.
Yeah.
And the problem is you need to know the flow.
So if I'm not wrong, it's based on the assumption that the flow itself is not inherently unsteady.
Oh, these are mean
Yes,
equations for
okay.
the mean or equations for the ensemble.
Yeah.
Yes, absolutely. Okay. Yeah, there you would have to. Yeah, if it's not unsteady, then just the concept of averaging itself becomes right. You have to do an ensemble, and then you can maybe write it. The same equation would be valid, but the average would be an ensemble average.
Yeah, that makes sense. Yeah, thank you.
Right. Yeah. Any other questions?
I was wondering, like, what are the suspected reasons for the additional tones in the LES versus missing that higher tones in the experimental?
The data wasn't reported up to that frequency. You can ask some number. That's all.
Okay.
Yeah, if you look at our spectra,
Right.
You get the peaks up
Yeah.
to the regime where they had it, and then we didn't see the data at the higher distance. So we just have to ask them to see, is it there, is it not there? We are just at that stage, but I thought we should report all our data.
So I guess I have a big picture question.
Yeah.
Maybe I don't understand, but the simulations gives you a prediction on when the inception of the bubble formation would happen, right?
Hmm.
Do you actually model the formation of the bubbles and how they can break down?
Each bubble.
Yeah.
In what I showed you now. So what went into it, into this prediction that you saw here is Mehdi did a bunch of separate calculations of actual bubbles
Yeah.
inside a DNS of isotropic turbulence. So he released bubbles of a certain initial radius and then watched them go through the flow.
See,
And then he tracked the events of where some of them, inception is really growing like this, right? So he tracked that and said, this is the frequency of at which a bubble of initial size R naught, say. Yeah, so something like this, right? So he then took those results and then obtained a frequency of inception. And he said, I'm going to represent it as being a function of the initial size, the absolute pressure that the bubble sees, and the nature of the turbulence in that isotropic turbulence. And when he said nature of the turbulence, since it was isotropic, took a Reynolds number and a dissipation rate. Now, the application of that table essentially to our flow involves making this sort of conceptual leap that inside every cell, you're so coarse, inside every cell, those isotropic results, at least for the frequencies, are valid. And so what we do in our calculation is, in our LES, we solve an equation for the subgrid scale kinetic energy that's dynamic. We solve another equation for the bubble density as a function of size that's dynamic. Those things then go into this table that we look up, and then that gives us a frequency that we plot.
so essentially it's simulating what the effects of the bubbles would be as well. So would it be a two-way coupled?
No. In fact, this is almost, you could say it's a post-processing step.
I see, okay.
You take the fluid flow and then you get these frequencies from a table.
Yeah.
The intent it is for it to be practical. So
I see.
when you simulate these flows with incompressibles. Now we have other work going on. Aditya has done that work where it's compressible, it's coupled. You have a large region of vapor, it's separate scale bubbles, they both give you the same thing, and that's a separate direction that's evolving. But here all you want is that what is that free stream pressure at which I start making noise? Okay. There aren't any more any questions online? I don't see any. Okay. Thank you very much.